So today's lecture is about combinational logic circuit. My name is Shiv Puri. I'm from the Department of ECE, Asansol Indian College. So in the previous lecture, we talked about the simplification of the Boolean expressions using K-map. Now we are going to talk about the combinational circuit, but at beginning, let us try to get an idea about the two different kind of the logical circuits, that is a combination and the sequential circuit. Okay, so any circuit can be configured under either combinational or sequential circuit. That is, there are actually two types of logic circuits. Okay, so combinational circuit is one whose output at a specified time is function of the input at that time. Output depends purely upon present input. That means basically there are two kind of circuits. Okay, one circuit will be having no memory. Okay, one circuit will be having no memory and another will be having memory. Okay, so no memory element required to store past input in case of combinational circuit. Its operation can be completely described by a truth table or Boolean expressions. Okay, whereas in case of sequential circuit, it is not so easy. That merely by using truth table and Boolean expressions, we will be able to get the idea of the functionality of the circuit. In that case, that means in case of sequential logic, we have to take care of the various states. Okay, as it is memory, so basically every state will also depend on the memory of the system, and eventually there will be a concept of present state and next state. Whereas in case of combination circuit, it is very easy to analyze. The circuits can be realized by using AND, OR, and NOT gates. Example: adders, subtractors, code converters, decoders, encoders, multiplexers, demultiplexers, parity checkers. All will be discussed in the succeeding videos. And you can see here. So in case of combination circuit, there will be n input variables and a very easy to analyze n output variables. A sequential circuit, as I told you, is a logical circuit whose output at a specified time is a function of inputs at that time as well as finite number of preceding input. Sequential circuit requires memory element because its output depends upon present as well as preceding states of elements. Basically, sequential circuit is a combination of memory element and combinational circuit. That means you can also say that it is a combinational circuit with memory. These circuits can be realized by using AND, OR, NOT gates and flip-flops, which is basically a storage elements. Okay, example: registers, counters, etc. So as you can see here, this is a block diagram of the sequential logic, where you can see here, along with this combinational circuit where you are using input and there is output, there is also a piggybacking from the memory element, and because as the whole system is dependent on memory, and therefore its uses, basically two major uses of sequential circuit in digital systems are as memories to store information while processing, so it stores memory, as control circuits to generate control signals. Okay. So synchronous sequential circuit. So basically there are two kind of sequential circuit. One is the synchronous sequential circuit and there is the asynchronous sequential circuits. In case of synchronous sequential circuit, it actually has a clock. It employs a clock, okay, by which it is triggered. All memory elements are clocked flip-flops. Okay, that means when there are n number of memory elements, okay, so all the memory elements will be triggered by a clock. So this kind of design, as all the memory elements are triggered by a same clock, so it is easy to design. And in digital system, that's why mostly synchronous circuits are used. Whereas in case of asynchronous sequential circuit, what happens is that sequential circuit do not employ clock, are called as unclocked or asynchronous sequential circuits. It is difficult to design and hence relatively uncommon. Now, one thing more I want to say over here, that in asynchronous sequential circuit, what actually is done is that the output of one flip-flop is basically the condition for triggering of the succeeding flip-flop. Okay, so and that's why the next memory, the next rather state will depend on the output response of the preceding uh, output state. So therefore, this is actually difficult to design compared to the synchronous sequential circuits. Okay. So let us talk of the combinational circuit, and let us take a first example of a simple half adder. So what half adder does, it logically adds, it adds 2 bits, okay, and it will not use any carry. So therefore, it is called a half adder. So A and B are 2 1-bit inputs, as you can see over here. A and B are 2 inputs, and the outputs are carry and sum. Okay, so as you can see here, see the chart. So AB are the input. These are the, as there are 2 inputs, there are 4 combinations: 0 0 0 1 1 0 1 1, and carry and sum. So let us first talk of the sum. 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, and 1 plus 0 with a carry 1. Okay, so this is the whole truth table of a half adder. So we can clearly see here that S is equal to, this is actually valid for these 2 expressions. Okay, so it is A bar B plus AB bar. Okay, so the sum is actually S is equal to AX or B, and C carry clearly is AB. As you can see here, A into B. Okay. Now drawbacks of half adder. Okay, drawback of half adder is it doesn't cater to carry, that is, it fails in multi-bit addition. It will add A0 and B0, but in next stage we have to add 3 bits, which will not be done by the circuit. Hence we require a full adder. Okay, so let us go to the full adder. As you can see here, to overcome the drawback of half adder, full adders is designed which considers carry, and that is the only thing which was missing in half adder for complete operation, or complete addition rather, and therefore the total inputs becomes 3 bits, 2 bits and a carry. The full adder produces a sum and carry value, which are both binary digits. It can be combined with other full adders. Okay, so as you can see here, there are 2 inputs, A and B. These are the carry from the previous bit, and it produces sum and a carry to the next full adder, if at all we require. So this is the truth table. So carry, input, and input, this one. So you can either you can keep the data like this, or no problem, even if you put it A, B, C, it is the same thing, just to take care of the bits. So 0 0 0 0 0 1 0 1 0, and you see here the whole, as it is 3 bit, so therefore there are 8 combinations. Okay, so as you can see here, it produces sum and carry. So 0 plus, so this is clearly 0, this is 1. So as you can see here, 0 plus 1 is 1, 1 plus 0 is 0, so it produces 1. 0 plus 1 is 1, 1 plus 1 is 0 with a carry 1, 1 plus 0 is 1 with a carry 0, 1 plus 0 is 1, 1 plus 0 is 1, sum 1, carry 0, and this plus this is again 0 with a carry 1. Okay, so 1 plus 1 is 0 with a carry 1, and 1 plus 1 is 0 with a carry 1, and 0 plus 1 is 1 with a carry 1. So you should inspect these numbers like this. Okay, so if you just add this like C bar B bar A plus C bar B A bar plus for one here for sum, I'm talking of sum, so C B bar A bar and C B A. Okay, if you just add this for these valid outputs, you will get the sum is equal to A XOR B XOR C. And similarly for carry, you will get this as C bar BA, C B bar A plus C B A bar plus C B A, and the whole element you will get like this. So with this, you will be able to get this whole circuit, okay, for a full adder. Interestingly, you can also produce an output with the help of half adders. This is the same thing, because you see here S is equal to A XOR B XOR C, and we know, we have just seen that A XOR B is nothing but a half adder, isn't it? So we will just simply put this half adder over here with two input A and B, or AB, whatever you say. It will produce a carry and a sum, isn't it? Now this S is also A XOR B XOR C, isn't it? So we will just put it here. Okay, we will just put it here. You can see here sum. So this will again be, because we know half adder is again between XOR between two bits. So one is the sum and another is the carry. So what, when we will get it is Sn, it will be this sum XOR C over here. Okay, and this sum is again A XOR B. So totally we will get A XOR B XOR C, which is the full adder sum. And similarly for carry, we will get this if you do this arrangement. Okay, so we will get this whole thing. Okay, so therefore you can also implement full adder using half adders. Okay, so as you can see here, this is a logical diagram of full adder. Okay, with the help of logic circuit, you require an XOR and an AND gate and another XOR with an AND gate, if you consider to be a two half adders. Okay, or simply you can go with this arrangement. Okay, so ripple carry adder. So this is also one of the things which you should know. It's a type of multiple bit adder. Okay, when multiple full adders are used with the carry inputs and carry output chained together, then this is called a ripple carry adder, because the correct value of the carry bit ripples from one bit to the next. To obtain it, n number of full adders are connected, as you can see over here. Okay, so here is it's an example of a 4-bit ripple carry adder. Why it is ripple? Because you can see here, this is a carry, this is two inputs, so it will produce a sum, and also carry which again goes to the next stage, and similarly at every succeeding stage we will get a sum. Okay, and in this way we will be getting a full adder ripple carry adder operations. Okay, thank you.